So welcome back to the second part. So where we left off the last part was we were looking at migration between Earth and Mars. And I posed the question of what would happen over time if we kept allowing people to move between Earth and Mars. And so that was our question. And what we want to look at is the answer. And what I've written here in blue is kind of telling me that the information that we're looking for is captured in the eigenvalues in the eigenvectors of my particular matrix. And so what I'm going to make use of the fact is that this matrix here that we found is actually diagonalizable. And so we know how to diagonalize matrix, and actually I'm just going to write out what the diagonalization is. I'm assuming that you guys are now experts of this, so you could double check this. And so here's my diagonal matrix. So remember, that's telling me what the eigenvalues of this matrix is. And then we have the inverse of my matrix P. All right, so I can think of this as PD times P inverse. Oh, you don't need to know about that. Go away. Okay, so continuing on. What we want to notice is, well, because the matrix P, which is the first matrix, is invertible, that means that the columns of P form a basis for R2. Okay, so since they form a basis for R2, what that means is we have that R2 can be written as the span of the first vector and the second vector. Okay, and you want to remember that these guys are actually eigenvectors, right? Because when we do the diagonalization, we're writing things, the columns of the matrix P come from the eigenvectors corresponding to the eigenvalues. So that's going to be kind of important for what goes on later. So now, because this is a basis, we can take our initial vector. Okay, so this is our initial proportion of the number of people on Earth and on Mars. We can write it in terms of our basis. And so I've done the hard work already. We can write this vector in terms of our basis, and it turns out to be 0.625 times our first basis element minus 0.25 times our second basis element. Okay, so we've actually taken our vector and written it as kind of linear combinations of eigenvectors of our matrix. Okay, so this is going to be important when we go to the next step here. So we've taken our x naught, and what we want to do is, well, we want to know is, well, what happens when I take A and I multiply by x naught? We already computed that, but instead what we're going to do is compute it by looking at what happens in terms of writing it in terms of its basis. Now, because this is a constant, when we multiply it through, we can rewrite it as 0.625 and then A times 0.61 minus 0.25 A times -1, 1. Now the point is that both of these vectors are eigenvectors, right? And we know what the eigenvalues are, so this gives me 0.625, 1 times the vector 0.61, and over here, the -1, 1, it has eigenvalue 0.92, so that gives me times the vector -1, 1. Okay, so it gives me this particular vector here. And just so you remember here, what I'm using is the fact that A times 0.61 is equal to 0.6 times 1. Right? We're using the fact that we have eigenvalues in order to make this work. And this value here is actually equal to the vector x1. Now we actually computed x1, but now we've written x1 in terms of our eigenbasis. And I could, collapse these things even further. I could combine the scalars together, but I want to keep them there for now so we can see what happens when we iterate the process. So if we iterate the process, we want to take A times x1, and we've computed x1 in terms of its basis, and we do it again. And remember, because these are scalar multiples, we can kind of pull them all the way out. So you have 0.625 times 1 times A times 0.61. So this is the vector. And here I'll have 0.225 5 times 0.92 times A times negative 1, 1, the vector 1, 1. And then using the same argument as before, well, these are eigenvectors of the matrix A, so I can replace this by getting 0.625. Now this becomes 1 times 0.6 times 1, so I really can think of it as 1 squared times 0.61 minus 0.25. And then when I multiply this vector by A, this vector is the eigenvector of 0.92. So I'll just again get a scalar multiple 0.92 times this vector. So in the end, I'll get 0.92 squared times negative 1, 1. And this is my vector x2. Okay, so now if you wanted to find x3, you would repeat the process. And what would happen is you would keep the same form, but each time you're just increasing the exponent corresponding to the eigenvalue. So for any k in our particular situation, what we're going to end up with is 0.625 times 1 to the k, 0.61 minus 0.225, 0.92 to the power of k, and then minus 1, 1. So here I have a formula for what the k's value is in my dynamical system, okay? And it's written, expressed in terms of the powers of eigenvalues and eigenvectors. Okay, so once you rewrite it in this way, we can go back to our original question of is, well, what happens as we let k go to infinity? Well, when you let k go to infinity of 1 to the k, that always is just going to 1. On the other hand, if we let k go to infinity for this guy, for 0.92, because this number is less than 1, as we raise its power, this part here will go to 0. So this part, whole part on the right-hand side, will start to disappear, right? And that's what I have written here. As k goes to infinity, what we have is 0.92k will approach 0. So that means that as we let k go to infinity, what we have is that x to the k will approach 0.625 times 0.61. And when we compute this out, what we get is 0.375, and then in the second spot I get 0.625. So the way to interpret what we've just did is saying that eventually Earth contains 37.5% of the population, and Mars will contain 62.5% of the population. And you'll notice that how we got this information is by rewriting everything in terms of our eigenvector basis, and we can easily see what happens in the long term. So we'll take a pause there, and I'll try to explain more generally what happens in the general case. Okay, so I'll see you after the short pause.